Good afternoon, ladies and gentlemen. It is a wonderful, well, kind of dreary spring afternoon as I'm recording this. So we're going to today take up our last topic for this unit, circular motion. So let's begin. Now this one's going to be a little bit longer, so if you need to pause at any time or even stop, remember you can do that at any time. Okay, so let us begin. So first things first, what is circular motion? Well, it's when things are going in a circle. It seems obvious. But because it's going in a circle, we can actually do things like measure the radius and then calculate things like the circumference, which is going to become super handy in a minute. Now, for the purposes of these lessons, we're going to assume that we're spinning at the same speed. Now, notice I said same speed, not same velocity. So we cannot say it's moving at the same velocity because the direction is changing. So let's take a look at our illustration here. This is the first, you see, this is where it is, the first position, it is moving towards the right. But to keep it from flying off to the right, we've got this string right here, which is actually pulling it in. And so when it comes over to the second position over here, you see that the direction has slightly changed. Okay, so we cannot say it's got the same velocity, only the same speed, because the direction is changing. Well, that's all well and good. So because the direction is constantly changing, we can say that it is constantly accelerating because acceleration is any change in velocity, including just that direction. And we know this because it would be otherwise it would be traveling, as we said, in a straight line, and that's according to Newton's first law. So from this, we can actually get a visualization of what our change in velocity is. And we're going to say, just as we do always, change in velocity is the final velocity minus the initial velocity. Or, because we're dealing with vectors here, we can actually just change the direction and then add them together. So change of direction is symbolized by a negative sign. So let's take a look at what this looks like. Now, so if this was my two velocities from the first example, here's my final velocity here, and this is my initial. Now, if I want to take the negative version of that initial velocity, I would just change the direction. So then if I'm adding them together, I would go take this one and then add this one right here, and here is my change in velocity. Now, what do you notice? You should notice that the change in velocity is going towards the center, which makes sense because it is being pulled by the string towards the center. So it says the acceleration, because the change in direction is going towards the center, so would the acceleration. And we refer to this as centripetal acceleration because centripetal means center seeking. And that is basically due to the string attached to the bob. Now, there is one thing here that we're going to take in a little bit, but I want you to refresh your memory as to what centrifugal force is. Now, because we've got an acceleration, we have to have a force because we cannot have an acceleration without a force. And this is according to Newton's second law. So if the acceleration is pointing towards the center, so must the force. So when we talk about a centripetal acceleration, we can also talk about a centripetal force. Now, here's where we're going to talk about the difference between centripetal and centrifugal force. Now, if you will remember the idea of a centrifugal force, that's the force that you think you experience whenever you're spinning, the force that pushes you out. Now, as we've just talked about, this is not what happens. Instead, we have a force going in, not a force going out. So we have a centripetal force, not a centrifugal force. Right? So we do not have this force. Okay, so we're just going to stick with our centripetal acceleration and our centripetal force because we've proven that the force is directed towards the center. Okay, now another thing to realize is that centripetal force is not necessarily a force of its own, Rather, it's more like a net force because it can be caused by multiple different things. So for example, when we're talking about the moon, that can be caused by gravity. If we're talking about our bob on a string, we're talking about the force of tension. But we can say that our centrifugal force in one case is a gravitational force. Okay. Now, you might also notice, because the bob is going around in a circle, that it will repeat itself over and over and over again. And because we refer to this, because it is repeating itself periodically, we call this periodic motion. Now, other examples are pendulums or waves from Physical Science 20, or sine and cosine graphs from pre-calculus. So we call the amount of time it takes to go through one revolution or cycle as the period. And we call this seconds per cycle, but very often we just say seconds. Now, because we're essentially measuring time, we're going to choose a capital T as our period. Now, this is a special measurement of time, the amount of time to complete one full revolution or cycle. Okay, so in order to, now related to that is the idea of, instead of just how long it takes for one cycle, how many cycles we can take in a second. And so if we wanted to talk about that, we're going to talk about the frequency. So that's how often something repeats itself. And they are inverses of each other. And so we find it, if you remember from Physical Science 20, with this formula. T is equal to 1 over F, where T is the period and F is the frequency. So they're inverses or reciprocals of each other. Now, usually, if you remember from last year, our unit for frequency is simply the hertz, but that is the same as saying cycles per second. Now, we have other ways to represent that as well. Instead of hertz, we can have something like RPMs. Now, RPMs are revolutions per minute, but hertz are revolutions per second. So in order to convert them, if you're going from RPM to hertz, you're just going to take your RPM and divide it by 60. All right? Now, let's take a look at an example. So I want you guys to pause this video and take a read through, and then we will go and discuss it. Okay, so we are looking at buying a new computer, and the hard drive of the computer is a metal disc that spins around at 7,200 RPM. And so what this basically means is we've got 7,200 revolutions or cycles every minute, which means it could be 432 revolutions in an hour or 120 revolutions in a second. So if we wanted to put this frequency into metric units, what we're going to say is, okay, we're going to take our 7,200 RPMs and we are going to divide it by 60 to get 120 hertz or cycles every second. Well, that's pretty easy. What about this period? Okay, well, if you remember, the period is the reciprocal of the frequency, which is 8.3 times 10 to the negative 3 seconds. So it takes 8.3 times 10 to the negative 3 seconds to complete one revolution, which makes sense if it's doing 7,200 revolutions every minute. Okay, so let's apply this to some velocity. So let's start off with this formula that we all know. Now, but because we're talking about a circle, well, the distance that it travels is going to be the circumference. So if we combine those, we can say, you know what? The speed is going to be equal to the circumference divided by the time. And that will give us the speed. That is one way. However, what if we're not dealing with one, because we're talking about time here, and we got 2 pi r. 2 pi r is the distance of one way around the circle, or one revolution. So you know what? Instead, we should probably substitute in the period and go 2 pi r divided by the period. So I would make sure that I know that equation. So let's do a quick example here. We're going to determine the length of a student's arm if she can swing a pail around 5 times in a circle at 272 meters per second in 7.5 seconds. Well, okay, that's pretty straightforward. So let's quickly take a quick survey of what we've got here. The length of a student's arm, you know what, that's going to tell you that's going to be the radius, and that's what we're trying to find. So I'm just going to put a box there. Swing the pail around 5 times in a circle. And you know what? 5 times in a circle. Okay. And we got a speed there of 2.72 meters per second. And we've got a time here. In those 5 times around the circle in 7.5 seconds, you know what? If I divide that by 5, I'm going to get 1.5 seconds. That's going to be my period. So I should change that to a capital T. Okay. So we just use the same formula. So I've got V is equal to 2 pi r divided by the period. So I'm just going to put some numbers in and do some algebra. So feel free to pause and do that. All right, so if you do that, you should get a radius of about 0.65 meters. Now keep in mind that pi is a number, and I just use the pi function in my calculator to tell me that. Okay, well, no, that's all well and good, but you know, we progress beyond just describing the speed. We know that there is some acceleration, so we should be able to describe that as well. So let's describe that. So we already know that centripetal acceleration points towards the center. And there's a whole big long proof, but you know what? Because we're just sort of doing this online, I'm going to simplify this like so. Okay. And this is going to be my velocity squared over my radius. Now we only use the magnitude of the velocity because the direction is constantly changing. So we're using the speed. Okay. So let's do that. So what is the centripetal acceleration of a person driving a car in 60 kilometers an hour? Okay, a quick conversion there will mean that the speed has become, give me a moment. All right, 16.6 meters per second. And then my radius is going to be 120 meters. So it's super important that we've got our speed in meters per second. So if you remember, you're just dividing by 3.6. Okay, so let's use our formula here. So centripetal acceleration is equal to V squared over R. Okay, so why don't you substitute things in and simplify. I got 4.63 meters per second squared. All right. Now, you can also combine the velocity formula from earlier with the centripetal acceleration formula to get an extra formula, something that might make it a little bit easier. All we did is we took our velocity formula, we substituted in for V, so we had to square it and then simplify some stuff, and we got this formula here, as you can see up above. So let's do a quick example using that one. What is the acceleration of a horse running around a circular racetrack with a radius of 37 meters once every 12 seconds? So first of all, let's get this set up. I'm finding the acceleration, and the track's got a radius of 37 meters, and going once every 12 seconds. So that tells me that's the period. Okay, why don't you pause, use the formula, and see what you get. Okay, so here's my formula. Now the tendency here is to forget to square the pi, or at least that's the way it is for me. But if I do that, what I'm going to get is I'm going to get 10.1 meters per second squared. So if I substitute everything in, I should be getting something resembling this. Okay. Now, let's take a quick little look here. Another way you can look at this as well is keep in mind that frequency is equal to 1 over the period. So if I have a period on the bottom, I've got 1 over period. So I could say that for each one of those, I can substitute that in for an F, getting this formula here. Okay, so that's all well and good, but let's take a look at some force. All right, so centripetal force. Now, we're just combining a couple of formulas here. We can easily say that force is equal to mass times acceleration, Newton's second law. That works just fine. We can combine things using that acceleration formula that we had earlier, that v squared over r. We can substitute that in and get this formula right here. If we want to use the other acceleration formula, or we can get this formula right here. Okay, so let's use this as in an example. So here's the setup. I want you to pause and give this a read. Okay, let's say for the sake of argument that we've got a speed of 10 meters per second. Okay, and from the question, I got a mass of 100 kilograms, and I got a radius of 8.80 meters. Okay, so let's put this in here. My centripetal force is going to be equal to mv squared. Why this version? Sorry, mv squared over r. Why this version? Because I have a v and an r. If I didn't have v, I wouldn't use this version. Okay, then I just substitute these values in, and I should get 1140 newtons. Okay, I want you guys to try for 15 meters per second. So you should have gotten 2560 newtons. Okay, now let's use a slightly different formula. Let's determine the centripetal force acting on a 100 kilogram mass man in a 8.80 meter radius centrifuge if he's spinning at 15 RPM. Okay, let's set this up. The mass is going to be 100 kilograms again. The radius is 8.80. And now we get a speed of, where was it here? 15 RPM. But we know we can divide that by 60 to get our speed of 0.25 hertz. Sorry, that's our speed. That's our frequency. Oh my goodness. So because I got the frequency, I am going to find the period. I could have used the formula with the frequency, I suppose, but I always like to use the period. Mostly because it's easier to work with not decimals. All right, so I'm just going to use this formula here. Now, like I said, I could have used the formula with the frequency. I chose to use the one with the period. .2170 newtons. All right, that's all I've got for this whole unit. So your practice here is going to be, you know what, make sure that you give this one a try here, circular motion practice number 11. And then when you're done that, please make sure you are done week 3 so you can actually go into the week 3 assignment. Please either submit it on Teams or email it to me, whichever you prefer. Please do me one small favor though, if you are taking pictures of it to send to me, if you could make sure that they're all rotated so that way I don't have to tilt my head to the side. It just makes marking it just a touch bit easier. All right. Thank you very much. Have a good weekend, and we'll see you guys next week.